Chapter 7.1 is the integration by parts. Now, integration is it's a noun basically for taking the antiderivative. So, integration, we're taking the antiderivative in parts. Now, this is another method that we learn, and it is to take care of, when we take the derivative, it is to take care of the product rule. Okay? So it is what I consider the anti-product rule. So let's review what the product rule actually was. The product rule was when taking the derivative of a product of two functions, we get the first function times the derivative of the second plus the second times the derivative of the first. Another way to look at this is the antiderivative of this full thing here, this line, should equal to f of x times g of x, right? If the derivative of this equals this, then the antiderivative of this should equal to this. I'm going to add the dx, and I'm actually going to split this up into two integrals this way. And then what I'm going to do is I am going to solve for this, because we want to go backwards and we want to take care of this product rule problem. So I'm going to solve for that function right there. So the integral of f of x g prime of x dx, right, is going to equal to f of x g of x minus the integral of g of x f prime of x, right, this one. This is essentially the integration by parts. Okay, this is really long and complicated to memorize, so here's what I'm going to do. I'm actually going to rewrite this. I'm going to shorten this. I'm going to do some substitutions here. So I'm going to make u equal to f of x, and I'm going to make v equal to g of x. Okay, so the derivative of u with respect to x is going to be f prime of x. I'm actually going to multiply both sides by dx, so du is going to equal to f prime of x dx. dv is going to equal to g prime of x dx, right? And then I'm going to replace all of this here. I'm going to simplify this a bit. So f of x is going to be the integral of u. G prime of x dx is here. G prime of x dx is dv. And it's going to equal to f times g, or u times v, minus the integral of g of x, which is v, times f prime of x dx. F prime of x dx is du. Okay? Now this is the formula that's much easier to memorize, though it's the same thing as this. They're equal. Now let's talk about when is it useful. When is it actually useful to take the integral by parts? When will it actually help? So if you take a look here, you have two functions, an f and a g. Two functions here, f and a g prime, a u and a dv. Okay, where you have to eventually, this will take care of itself, but this part is what you have to worry about. You actually have to take the antiderivative a second time as part of the formula. Now when you take that antiderivative a second time, you want to make sure that second time is easier than this first time, right? So what makes it easier? Well, it looks like what's entering that second integral is going to be the derivative of one function has to enter the second integral, and the antiderivative of the other function must enter that second integral. And when they both enter, so the derivative of one and the antiderivative of the other has to enter the second integral, and that integral must be made easier. So let's take a look at example 1. It's the perfect example. Okay, the integral of x sine x. Now, why is substitution no good here? Well, substitution, remember, was the anti-chain rule. There's no composite of functions here. Du will equal, if I do a u sub, u will equal x. The derivative of x is just going to be 1. It's not going to help here. It doesn't exist on the outside. What does help here is integration by parts, because like I said, the derivative of one and the antiderivative of the other second one must enter a second integral together and make it easier. Okay, the derivative of x is 1, antiderivative of sine x is negative cosine x, and those, when they enter a second integral together, it will make it easier. So that is why integration by parts is good. Now those two questions in your notes, please make sure you write in there, you answer those questions, and that's how I'll know that you actually didn't just copy a screenshot. Alright, so let's try this. What will this look like? Well, it's going to be, I'm going to set u, one of the functions equal to u, and I'm going to set the other function equal to dv. Okay, so I'm going to do that over here. So u is going to equal to x, and then dv is going to equal to sine x dx. Please make sure you include that dx in there. And then what I need to do is I need to find what du is, because I'll be using that here. So du dx is equal to 1, but that dx I'm going to multiply to the other side. I need to solve for what v is, because we're using that in the formula. So the antiderivative of dv is negative cosine x. And then once you've set that up, it's just the formula. So the integral of u dv is equal to uv minus v du. So uv x negative cosine x, uv minus the integral of v du. So v is negative cosine x, du is dx. Okay. Now again, why did this work? It worked because the derivative of one function entering the second integral and the antiderivative of the second function entering the second integral actually made this integral easier. So negative x cosine x, the antiderivative of cosine x is positive sine x, and here is where we add our plus c. And that's it. It will get easier, so once again, just memorize u dv is equal to uv minus v du. U dv is equal to uv minus v du. Let's try example 2. Example 2 is the antiderivative of natural log of x dx. The derivative of natural log is 1 over x. Let's see what to do here. So what we're going to do is, again, we're going to make this look like the integral of u dv, right? We're going to make those parallel, and then that's going to equal to uv minus v du. Okay? So one of these I have to set equal to the u, and one of them I have to set equal to dv. Whatever I set for u, I have to make sure I can find the derivative, and whatever I set equal to dv, I have to make sure I can find the antiderivative. So I'm actually going to set this function equal to u, and then this equal to dv. Okay, so u I'm going to set equal to the natural log of x, dv I'm going to set equal to, dx. Take the derivative of u with respect to x, du dx, I'm going to get 1 over x dx. The antiderivative of this is going to equal to just x. And then it's just plugging into your formula. So if this is u dv, it's going to equal to uv x natural log x minus v du. And notice again, the derivative of one function with the antiderivative of the other made the second integral a lot easier. And the antiderivative of 1 is just x. And then I add my plus c. It's an indefinite integral. Yes? Next one. Again, it's uv minus v du. U dv is equal to uv minus v du. Right? So one of them I have to set equal to u, One of them I have to set equal to dv. Now, if I set this equal to u, the derivative of this will become 2t. I'm going to say I'm probably going to have to do it again because I want it to simplify some more to regular, just a constant of 2. Anyways, I'll show you. So e to the t dt I'm going to set equal to dv so that I have it exactly parallel u dv, like here, like so. So then I'm going to set u equal to, I set u equal to 2t squared, dv equal to e to the t dt. Because the derivative, when I take the derivative of u, it must simplify. If I set e to the t equal to u, taking the derivative of it will not simplify. It'll keep e to the t. So what I'm going to do is, it's going to be du, take the derivative, is 2t dt. The antiderivative of this, v, the antiderivative of e to the t is just e to the t. Right? So it's going to be uv minus v du. E to the t, 2t dt. Right? So, did it simplify my second integral? It kind of did. It brought it down a degree. Right? If I made this t squared equal to dv, it would have brought it up a degree. It would have become t cubed, and that's not what we want. But it looks like there's nothing that I can do here except do another integration by parts. So what I'm going to do here is I'm going to make this now equal to u again, and all of this equal to dv. And I'm going to do integration by parts again. So u will equal to t here, and dv will equal to, again, e to the t dt. Du will equal to, now it did simplify just to 1 dt. Antiderivative of this will be e to the t. I'm going to leave my t squared e to the t minus 2, and then I'm going to take the integral of this inside here, which will be uv minus the integral of v du, e to the t dt. And now it really does look like I've simplified it where I can just find the antiderivative just once. So that will give me t squared e to the t minus 2 quantity t to the t minus e to the t plus c. Yes? So t squared e to the t minus 2t e to the t plus 2 e to the t plus, you can either write 2c or you can just leave it just a constant, at least at this point. And that would be it. There is a faster way. If this was, for example, t to the 4th power times e to the t, we would have to do integration by parts 4 different times. Instead of doing that, there is a nice pretty chart that we can make, but we'll go over that nice chart in class. And that's it.